What we're going to prove today is called the triangle inequality. It states that suppose Z and W are two complex numbers, or Z and omega are two complex numbers, so they're going to have real component, complex component. The idea is that if you take the modulus of the sum of Z and omega, it will turn out to be less than the modulus of Z plus the modulus of omega. So one way to think of that is that if you have, let's say, Z and let's say omega, then this in turn would be Z omega. Do you agree? It's the distance between the two. Or it's the sum of the two vectors and then the length of them. But if you got Z and omega and you laid them out flat together, so the distance of...
What does that say then? Complex.
Complex.
Yeah.
We have the Z there, and then you have omega there. See how they're going to be longer? It's just a representation, but we called that. So this is what we're going to try and show. Alright, now this one requires a few leaps of faith. We're going to use these two properties up here at some stage in this show to be able to get to this point here. Now, the first thing I'm going to do is I'm going to pick the left-hand side and say our left-hand side is Z plus omega. Are we cool with that? And then next thing I'm going to do is I'm going to square both sides. Are we okay with that? And then what I'm going to do is I'm going to expand it out. However, I'm going to use the first identity on the top right of the board. When I expand it out, I'm going to do that. We cool? All right, next step. I'm going to bring the modulus inside, the conjugate inside on both of the moduli. Is that all right? And then we're going to expand it out. So this is going to be Z modulus plus Z modulus of omega plus Z modulus multiplied by omega plus omega, like so. Is that all right? Do we see what's happened? Next step. What we're going to do is we're going to go from what we did to get to here, we're going to go from there back to there with these guys. So these are just going to turn back into Z squared like so. And then we're going to prepare for the next transformation. See how we've got these two terms in the middle here? I'm going to do the conjugate twice over there. So I haven't changed its value, I've changed its appearance. This is going to be beneficial because it leads into what we did just moments earlier. That's going to become Z, that's going to become omega bar, that's still conjugated, and this is like so. Now, here's where we draw our attention. These two. What we're going to do is we're going to use that second rule on the top right of the board to reduce this into its real components. We're going to be okay with that, Nick?
Oh yeah.
Attaboy.
Wait, how do you just remove one of the bars?
Because I brought this bar down on the Z, so that reverse conjugate again.
Oh yeah.
And then I brought this down on the omega, and that's why the omega got the bar, and the one bar just stayed at the top.
Yeah, makes sense.
Yeah, so we took the double conjugate just so we could change its appearance. Okay, next step, we're going to apply the second identity where this is simply going to be two lots of the real component of z and omega bar. But the thing is, it doesn't matter if it's omega or omega bar.
No, because it's modulus.
It doesn't really matter. Seem alright? Okay, and here's where we have to take a slight diversion. We're going to do it in blue. Have a look at this part here. This is where I got stuck for a little bit. Suppose we have, let's say x is a complex number. And let's say it's a plus ib. If we've got x equals a plus ib, then the real component of x is just going to be a. And if the real component is just a, we know that this is going to be less than or equal to the square root of a squared. Because a can either be the positive, in which case it's equal to, or it can be the negative, in which case it's less than. Do we agree? Do we follow?
Oh yeah, kind of, not really.
So the real component of x is a. Do you agree with that?
Yeah.
And say I squared it and then I square rooted it, would you agree that that statement holds true?
Mm-hmm.
But imagine if a was negative, so it was like -1. Would that, or would this statement hold true still?
No.
No. So what we say is there's two conditions. One where a is positive, where it's equal to, and one's where it's negative, where it's going to be less than. Is that cool?
Yeah.
Okay, now, you know what also is less than? If we also threw in the complex component and did the square. So we took the actual length of the whole thing. It's less than in both cases now, isn't it? A is always less.
Yeah.
But what is this equal to? Well, it's equal to the modulus of x. So all of a sudden we've turned something that was equality into inequality. Do you guys agree with this? You've got to tell me now if you can't see it, because this is what we're all hinged on.
Can you go through it all the time? Yeah, I reckon you can explain it one more time.
Yep. So we've just said, suppose we've got this complex number x, and x has a real component and an imaginary component b. Now the real component of x is a, and we know that a is less than or equal to the square root of a squared, or the length of a. Because it could be positive, in which case it's equal to, or it could be less than in the case that it's a negative value, because this will make it come out positive. Now, here's where we take a slight, I guess, not leap of faith, but we just point out something that seems so obvious that it's sort of why. We've added in the complex component of the number here. So we're saying that A is A is either equal to or less than this plus this. Now, if this number was purely real, as in the B component was 0, then that would be zeroed out, and our statement's still true. Is it correct?
Yeah. Yeah.
Now, suppose that A is negative, then again, we're still correct. Now, suppose that B is non-negative. A is going to be less than the magnitude of its complex number. Do you agree with that?
Yeah.
And because of that, we can say that the real component of x is going to be less than or equal to the length or the modulus of its complex number.
Yeah. So the only way that A is equal to the modulus of x is if a is positive and b is 0.
Bingo. Do you agree?
But anything else is less than.
Anything else is less than, and we can have a look at that case when we're done with this as well, because it's really interesting, especially when we're studying vectors, because we see this again in vectors. So we're all cool with that blue?
Yeah.
All right, wonderful. Now, here's where we get to make a little bit of headway. We still have the square of the left-hand side, and we know that it's going to be this plus 2 lots of the real component of z and omega plus the modulus of omega squared. Now have a look at this. We can get this guy and we can apply this here. Rather than having 2 lots of this, we can have 2 lots of, and we will say the real component of that. Are we cool with that?
Did anything change?
Almost. Oh, sorry. No, I didn't. Because I didn't do what I was supposed to do. Where are we? We're going to take the modulus of that. So we're going to go 2 lots of that, I believe. Is that okay? So this, we have a perfect square situation.
So how do you just remove the real component? Why'd that get rid of it fully then?
Because it's equal to or less than.
It's always equal to or less than. And sorry, I needed to change these as well. This is going to be, did this get, from here to here, did this get, is this bigger than that or is this less than that?
Less.
This became bigger or less?
Less.
Bigger.
Bigger. Because it's only just a real component. So because of that, we've got a perfect square. What we're able to do is and then if we square root both sides, and then there you go. Is that all right?
Yep.
So this has popped up the last 2 years, where it's either been in the internal, where part of a question hasn't required you to, they've given you somewhere along here or here, and you've had to identify that it was this relationship. So you just state that. It might be, say, show that something's larger, and you just have to be able to see there's a triangle inequality, and it's one liner, triangle inequality.
You write triangle inequality.
Yeah, you just, last year that's what they had to do on the internal.
So
They had to identify the triangle inequality relationship and just state triangle inequality.
Why is it called a triangle inequality?
Do you
Vector,
remember the diagram I drew?
yeah, that's the only reason.
Yeah. And in the external, I think it was 2 years back, it showed up.
Oh, so we're guaranteed to get a question on this.
Well, it seems that the people writing the papers really like this. If it doesn't show up in complex numbers, it will probably show up in vectors. So we'll see this again for vectors.
Ah, okay. Yeah. Well, so we're
How
going
did the square disappear? Oh, okay, you got it. Boom.
Yeah, square root of both sides.
this is going to the picture,
Yeah.
I put this on the help sheet. There's another one we have to look at as well where it's a difference between the two, but we'll do that next lesson. It's only 1 or 2 extra lines.
So is this not in the textbook? No.
No.
Oh, why not?
You probably got added to the course later, or the people who did the textbook just didn't put it in.
Alright. Makes sense, I guess.
There's a few things that aren't in the textbook that we have to cover this year.
Yeah, alright.
Is that most of vectors?
Yeah, there's a large portion of vectors. We look at how model spheres and the intercepts in spheres. So a line cutting a sphere.
Yeah, that sounds pretty confusing.
Are we okay with this?
Somewhat.
Took me